In this video, we're going to come up with a rule for what we call p-series. They're any series, infinite series, that have the form 1 over k to the p, as k goes from 1 to infinity, by studying improper integrals. So let's go ahead and do a basic one first, just to get the hang of this. So if I want to do from 1 to infinity of 1 over x squared dx, first thing I'll do is change it to a proper integral with a limit. So I got the limit as b goes to infinity of 1 to b of 1 over x squared dx. And a lot of times what we'll do in this case is we'll rewrite that. So limit as b goes to infinity, 1 to b of x to the minus 2 dx. And now we'll use our antiderivative power rule. Increase the exponent by 1. So x to the negative 1 divided by the new exponent, negative 1. Now we still are going to be taking the limit as b goes to infinity, and we still need to incorporate our limits, which are 1 to b. Now at this point, it may be easier to rewrite this with a positive exponent. So we're going to be looking at the limit as b goes to infinity of negative 1 over x, because it's an x to the negative 1 and it needs to be made negative, from 1 to b. So we have the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. This is the only piece that depends on b. This is the only piece we have to take the limit of. As b goes to infinity, this term is going to go to 0. So we end up with 0 minus a negative 1, or 0 plus 1, or 1. So what that tells us is this improper integral converges, so we can conclude that the series from k equals 1 to infinity of 1 over k squared converges, and we did it by the integral test. Now, we want to generalize. We want to know, hey, if we know what p is, can we tell convergence or divergence? So we're going to do real similar steps to what we did here. It's just going to be more general because we don't know p. So we do the limit as b goes to infinity. And I'm going to combine a step here from before. And I'm going to rewrite that as x to the negative p dx. So now we'll go ahead and do our antiderivative, same exact way we did before. Limit as b goes to infinity. It's going to be x to the negative p plus 1 over negative p plus 1 from 1 to b. Now we're going to go ahead and put in our limits, and then we'll go from there. So we have the limit as b goes to infinity of b to the negative p plus 1 over negative p plus 1 minus, now we'll plug in 1 to the negative p plus 1 over negative p plus 1. Now, there's one case I want to talk about right now before we go any further, and that's if p equals 1, because what you can see is we'd end up with a 0 here, and we'd end up dividing by 0. If p equals 1, we would have gotten 1 over x, or if p equals 1 here, we'd get 1 over k, our harmonic series. We've already seen the harmonic series diverges. So we already know if p equals 1, then we know it diverges. So we're testing for p greater than 1 or p less than 1. Those are the cases we don't know yet. Which means as long as p is not 1, this is always going to be equal to 1. So this is the part that we are concerned with, and this here is just a constant. So let's start to pull this together. So I'm going to take that out front, 1 minus over negative p plus 1, and I've got the limit as b goes to infinity of b to the negative p plus 1, and like I said, at the end we'll have that minus 1 over negative p plus 1. So this is the part we are concentrating on right here. That is what we need to know. If that part converges, the whole thing converges. If that part diverges, the whole thing diverges. And we have to decide when. Well, let's look at two cases. We know P equals 1 we're not concerned with. We already know that diverges. If P is greater than 1, okay, let's see what happens. We have the limit as B goes to infinity of B to the negative P plus 1. If P is greater than 1, what that means is this is going to have a negative exponent. It's going to be B to some negative exponent, which we could rewrite as 1 over B to some positive exponent. In fact, let's go ahead and do that. Limit as B goes to infinity of 1 over B to the P minus 1. Alright, so as long as P is greater than 1, this is going to have a nice positive exponent, which means the denominator is going to grow, the numerator is going to stay at 1, so this is going to equal 0, and thus it's going to converge. That makes sense because notice we saw that when P was 2, greater than 1, it converged. Now, if P is less than 1, let's go right to this step and see what happens. Limit as B, actually we can do it from this step here. Goes to infinity of B to the negative P plus 1. If B is less than 1, say a half, well, then we'd be looking at B to the negative half plus 1, so the positive half, or the square root of B. That's an increasing function. So if P is going to be less than 1, we're always going to have an increasing function here. So in this case, the limit does not exist, or we could say it's infinite. Thus, the P series only converges if and only if P is greater than 1. And that's going to be a test that we can use from here on out. If we have a series of this form, we can say it's a P series, and we know it converges if P is greater than 1.